especially George and Ravi, for the invitation. It's wonderful for me to be here. I gave a lecture here in 1991 in the mathematics department. And for those of you who may remember the 60s or did research on it, one of the instructors of mathematics was Mario Savio, who is one of the most radical of all students of all time. So you can look him up on Google if you want to remember that. So it's wonderful to be here again, and I want to thank you for the invitation. The subject I'd like to talk about today is called Benford's Law. If you want to look it up in Google, Benford's Law is a good way to start. I want to start with two concrete examples here. Start with any positive number. Doesn't have to be an integer. Start with any positive number and repeatedly multiply it by 2 or 3. And you get to pick. So here I start off, for example, with 4, then 12, multiplied by 3, then 2, then 2 again, then 3. So you can choose the 2 or the 3 each stage. The question is, what proportion of this sequence begins with a 1? So you have a long string of numbers here. You get to choose the 2 or the 3 you're multiplying by each time. And the question is, does it even have a limit? The second question here comes from somebody here in your department. This is a zero-sum game. So Ravi showed me this earlier this year. I'm a probabilist by trade, and anybody who's in the audience of the speaker who's a probabilist wants to know, when they walk out of there, how can they make money from some of their friends? So this is a game which was discovered by Ravi, and I'll tell you the theorem which is the basis for this, but here's the game. You can describe this game to 8th graders, to 8-year-olds almost. To 2 players, 1 and 2. Very simple. Each of them picks a positive integer, any way you want. You can flip a coin to get it. You can ask your friend how to get it. You can do it randomly, any way you want. You pick a number, I pick a number. And since I'm Mr. Nice Guy, I'm going to be player 1 here. Since I'm Mr. Nice Guy, if the product of these 2 integers we pick begins with 1, 2, or 3, then I win, say, $10 from you. If it doesn't, so if it begins with 4, 5, 6, 7, 8, or 9, 6 numbers, then I give you $10. So it's very simple. I'm a nice guy, so I'm going to only take 3 numbers, and you get the other 6. Okay? Now the question, several questions here. What is player 1's best strategy? What's my best strategy? What's your best strategy? So these will both be applications of some ideas. I'll tell you formal theorems, formal results later. There's 2 concrete things to think about. Start with any number at all, multiply by 2 or 3. You get to pick. You can do it randomly. You can always use 2. And the second one is you're going to play a game with your friend when you walk out of here and hopefully make some money. Okay? So I like questions. If anybody has questions at any time, just please let me know. So here's a short outline of what I'd like to talk about today. I want to tell you what Benford's Law is. I'm going to assume that most of you haven't heard of it. Significant digit law. Tell you a little bit about the empirical evidence and the history. Tell you about scale and base invariance. Deterministic sequences like Fibonacci sequence, Lucas numbers, stochastic sequences. It's random variables, sequences of random variables like the stock market. Some applications to computer science, so I reviewed some of those because this is the computer science department mainly. Some very beautiful applications to computer science. General applications, that will deal with the fraud. Right now the IRS is using Benford's Law, in California IRS and a national one, to look at your tax returns. So I want to show you where that comes into play. And then some open problems, some unsolved problems of some of my favorites. So let me tell you what the significant digit law is first. I'll phrase it in terms of floating point arithmetic. So when you're using a digital calculator to do scientific calculations, you don't work with this number. You write it as a mantissa times the power of 10. I'll assume for right now, I'll assume that your computers are using base 10. everything I say today will carry over to other bases, so if you have questions anytime, let me know. Oops. So the mantissa function, it just associates, so just recall the mantissa of pi is the same as mantissa 10 pi, that's 0.3141. Benford's law is a probability distribution on mantissas. So you can think about this, you're doing calculations, you look at your latest entry, your latest output of your algorithm, you're just looking at the mantissa, forgetting the exponent. You want to know what is the probability this number is, say, less than 1/2. Many different probability distributions it could be. Benford's law says it's a logarithmic one. And for a sequence of random variables, if you want to think of a sequence of numbers, you say that Benford's law, if you want to talk about Benford's law in that context, you look and see what proportion of numbers less than n had a mantissa less than t. And then you let n get large. Okay. So this is the one that's most often quoted, the most well-known one. It's the first significant digit. And I'm talking about base 10 here, just for the purposes of illustration. It says, Benford's law says that the probability of the first significant digit is the log base 10 of 1 plus 1 over d, that it's equal to d. Now the first significant digit is one of the digits 1 through 9. The second significant digit can be 0. 30, the number 30, has first significant digit 3 and second significant digit 0. So if Benford's law is in effect, then 30% roughly will start with a 1. 17% will start with a 2, decreases exponentially. Only 4.6% begins with a 9. This is just, so far I'm just telling you probability distribution. There's many other possibilities for the mantissas. It could be uniformly distributed. Sometimes they are. So now let me give you there's extensive empirical evidence. I'd like to give you just an overview of some of these. The one who first discovered this was Simon Newcomb in 1881 and published a paper in the American Journal of Mathematics. He had an easy time getting published. He was the editor of the American Journal of Mathematics then. It was a 2-page paper. It went completely forgotten until the 1970s. Benford, who essentially discovered the same thing in 1938, got very lucky. His paper was published adjacent to a paper by Hans Bethe that won a Nobel Prize. In those days, you couldn't just do Google and look it up and download it. You had to go look at the journal. People were looking up Hans Bethe's paper. By accident, you'd hit this one, they go, well, that's interesting. So it got more attention than it would normally. Now, both these people said the way they discovered it was this. They said, in those days, you didn't have calculators. When you did calculations, you had to use a book of logarithms. You can find those in historical archives now. They're this thick. They just have lists of all the logarithms and numbers you might want to look up. So both of them had occasion to be doing calculations. They went to the library, checked it out. Both of them noticed that before you opened the book, it was on the table that the pages in the beginning were dirtier than they were at the end. And they said, well, that's crazy. That means that biologists and sociologists and computer scientists and mathematicians are looking up numbers which start with 1 more often than they look up numbers starting with a 2. And 2 more often than 3, and so on. Then a great leap of faith said, well, it's a logarithmic law. Now, in computer science, of course, Knuth, now his recent editions also, I think 97 was the latest. I'm talking about volume 2 here. Knuth has a whole section in the Art of Computer Programming, Volume 2, on Benford's law. And the reason is this. Knuth is in the business of doing calculations, scientific calculations, or helping other people to do it. And he said, whether you like it or not, it's a fact. And when people are doing scientific calculations, 30% of the numbers start with a 1. 17% start with a 2. He said, if you don't believe it, just look at a farmer's almanac. But this is just a fact. Now, why was he interested in this? Because if you have information about the distribution of something like this, like a mantissa, you can use that. Later, new applications use it to detect fraud. Earlier application maybe to design a computer a certain way. Anytime you have information about the distribution of numbers you're working with, you can use that. Varian studied land use in the Bay Area here, how much land was used for agricultural purposes, how much for industrial. He found it fit Benford's law. This is one from physics, both of these. Physical constants ones, Burke and Kincannon. If you take your physics book and open up the inside cover, you see the speed of light, Planck's constant, Rydberg constant. Look at these constants. About 30% start with a 1. About 17% start with a 2. Again, alpha decay lives. Buck, Merchant, and Perez looked at all the substances which emit alpha particles, and they looked at their half-lives. And this varies tremendously from seconds or microseconds to hundreds of years. And they just looked at the numbers. 30% roughly start with a 1. Negrini made a spectacular application in 1995. He noticed, he's an accountant, did his PhD in the University of Cincinnati, and he found that true tax data follows Benford's law, certain categories. Whereas, if you're just faking it or getting creative at tax time, chances are it doesn't follow Benford's law. That's essentially the test I'll describe a little later. That doesn't do a real easy test. Leif saw that the stock market follows Benford's law. There's different aspects. The Dow Jones Industrial Average, the individual stocks, there's much evidence of that. I'll give you mathematical explanations for all these things so far. Molecular dynamics, this was in physics. Let's see, how many people have heard of the inverse symbolic calculator? Anybody here? Okay, one person. I just learned about it recently. Somebody came to me and said, well, that follows Benford's law. What is it? It's this. Suppose you're doing a scientific calculation, and your computer tells you the answer is 0.865255979, blah, blah, blah. You know, what is that? Well, you go to Google, you look up inverse symbolic calculator, you plug in the number you've got, and it tells you, oh, that number, that's simple. That's E over pi. So it has listed almost hundreds of thousands or millions of entries. So if the number you're looking at was really cosine of pi over 6 times E, then you'll find it in inverse symbolic calculator. So there's some evidence here that they try to include all numbers that people are using. So about 30% begins with a minus, 17% with a 2, and so forth. In computer science also, digital images. It's just some very new applications. People in France, Julian in France, Abdallah and co-authors in New Mexico and Spain, and they're using Benford's law to address that. So here's some of Benford's original data. Here's the logarithm book. Here's a copy of his paper that he published. It's so famous now. Notice the evidence shows that he spent 2 to 3 years just gathering data. He just went from friend to friend, a colleague, walked down the hall, what are you interested in? That guy would say, well, I'm interested in baseball. So he put American League stuff in there. Well, he had another friend who was studying rivers, areas of rivers. He had some friends, maybe mathematicians, he looked at square root tables. Newspapers up here, he just took numbers out of newspapers. Now to show you, this was in 1938 that he published his numbers out of newspapers. What do I mean by that? Well, I took today's USA Today, so USA Today does not care about me giving this talk. They didn't set anything up. I circled every number on the front page. Page numbers, advertisements, 800 numbers, I don't care what it is. There's 103 numbers on today's USA Today that I saw. 35 of those started with a 1. 5 of them started with a 9. So the predicted value was 4.6%. Here was 4.8% for 9. So there is something happening there. I want to tell you also a theorem that is the best explanation for that I know of. So you can double check me on that if you want. So here's a short histogram of several different categories of data. This is Benford's data of newspapers. This is the 1990 census. The 2000 one also satisfies it. I just want to take something that had already been published. This is from the Greeny's data. He looked at the populations of the 3,141 counties in the United States. And he looked at the first digits. So normally you would not put Los Angeles County with 15 million people in the same category as some little county in North Dakota with 150 people. But they both have the same significant digits. They both start with 1, second digit 5, maybe it's zeros after that. So they found that within two or three decimal points it fits Bemford's law. I'll give you a mathematical theorem that helps explain that. In the Dow Jones, this is again Lay's article. I want to say a few words about the history of the problem. It was treated as a gimmick for many, many years. Some things follow Bemford's law and some don't. Look at a phone book. Phone book doesn't follow it. No numbers start with a 1. 1 is an access code. The phone book doesn't satisfy Bemford's law. The natural numbers, the positive integers, do not satisfy Bemford's law because let's look at the numbers that start with a 1. Well, you have 1, the first one, and then you go through a dry spell of 9. You don't have any. Then you have 10, 11. You have 9 of them in a row. 10 of them in a row. And then you don't have any for a long time. And then you have more. Well, you'll see that the limb soup, that is, the numbers get as low as 1/9, the fraction that you've had, depending on when you stop, and as high as 5/9. So it keeps oscillating. You go through dry periods and periods of water one. So the numbers don't, the natural numbers, the positive integers do not satisfy. So that makes it more intriguing because many data sets do and some important ones don't. Try to understand why, when, can you predict when it happens? Now there are many complicated explanations. People have proved this, mathematicians, magicians, astronomers, physicists, statisticians have tried to give different arguments why it's true, when it's true, but none of the classical explanations were true probability. By true probability, I mean the numbers are always between 0 and 1, and it has to sum to 1 if they're disjoint. The probability, if you're flipping coins, the probability stops at time 1, plus the probability stops at time 2, etc., has to be equal to 1. Now, one of the key ideas that was studied maybe 30 years ago, but there were no correct proofs for it, was the following notion. It's beautiful. It goes back to Hamming. It was originally, I guess, conjectured by Hamming, the computer scientist, mathematician. And it's the idea is this. First of all, you have to identify what classes of numbers you're talking about probability of. That's always important. If you're studying probability or any function, you need to know what's the domain of the function. Probability of what? Let's make it concrete. The problem mathematicians had in the past was they used the natural Borel sigma algebra. The natural sets. An interval is always something you would talk about. But an interval in a mantissa doesn't make sense. This d is equal to 1, the first digit is equal to 1, is not just a single interval. It's that interval, and then I can shift the decimal point to the right or left. So it's an infinite number of intervals. There's no single interval that is among the sets that you want to look at the probability of. So you have to identify the correct domain. And this is called the sigma algebra. It's just talking about the class of sets or events if you took undergraduate probability. It has some interesting properties. If you have a set S, which is one of these sets that you can take the probability of, then you multiply by base B. If B is 10, you multiply by 10, you get the same set. If you take numbers which have first significant digit equal to 1, and you multiply by 10, first significant digit is 1. It's scale closed. If you multiply by 3, then you get then the new set is also a set which can be described by significant digits. And the curious one here, and this is important for base invariance, is that if you take a set of numbers and look at the square root, so you look at the square roots of every one of the numbers in your set, that's also one of the ones you can talk about. The square is not. So here's several characterization theorems. So we'll say that a probability measure on real numbers, positive reals, I'm excluding 0 just for the talk, Zero, if you want to talk about zero, there's nothing interesting you can say. It's the only number whose first significant digit is zero, and it's true for all bases. If you want negative numbers, you can just take the absolute value. So I will just sort of concentrate on the positive numbers. And you say a probability is scale invariant if the probability of a set is the same as the probability of 3 times a set. So I have a certain probability I want to associate, for example, to the numbers which start with a 1. I multiply all those numbers by 3. Probability should be the same if it's scale invariant. Now the theorem which I found in 1995, this was conjectured much earlier. The idea goes back to Hamming for scale invariance, but there was no mathematical proof of it. And that's this, that Benford's law is the only scale invariant probability distribution on a mantises. It's the only one. It's also up to placing positive mass on the integer 1. It's also the only base invariant 1. See, 1 has a special place among different bases. 1 is b to the 0 for all bases. So that's a special case. Once you rule that out, say, okay, things can be 1, but if they're not that, then it's Benford's law. Now this idea, this theorem right here, the first part of it, is the key to Ravi's game that I told you about. Here's how you can make money from your friends. You tell them, look, you pick a positive integer, I'll pick 1, and we multiply them together. It begins with 1, 2, or 3, then I win. 4, 5, 6, 7, 8, or 9, you win. Sounds like a deal. Do the calculations, I win 60% of the time, more than that. What's my strategy? I pick my numbers according to Benford's law. Why is that a good strategy? Because no matter what you pick, I pick my Benford's law. This theorem says if you multiply by anything, it stays Benford's law. So you can't destroy my strategy. I already know what the distribution is going to be of the first significant digits. So I win if it starts with a 1, 2, or 3. Add those up, it's more than 60%. So it's just it's a wonderful application of this theorem, and very surprising one. Peter Allard showed another thing that Negrini noticed was if you look at data, you write it all down, and it follows Benford's law, he made the crazy observation that only an accountant could make. But looking at numbers all the time, he said, look, if you add all the numbers starting with 1, you get the same thing as if you add all the numbers starting with 9 or with 8. If you add all the numbers starting with 1, 1, you get the same thing as if you add all the numbers starting with 7, 7 or 3, 9. Well, in fact, that characterizes this law. This is the only distribution that has that property. So this was also discovered by Negrini, but proved mathematically by Peter Allard from Amsterdam in 1997. Might add that was his master's thesis. It's one of the nicest master's thesis that I ever saw. Very beautiful result. So now I'm going to show you some mathematical reasons why some of these things are true. I'm not going to give the details. I'm going to give some examples, focus on examples, and I'll show you the actual full-blown theorems. So this has been known for some time. If you take any number, you look at the sequence of powers of 2. It follows Benford's law. You can find a simple proof in doublets. Fibonacci sequence follows Benford's law. N factorial follows Benford's law. So there's some mathematical sequences that follow Benford's law. Many don't. We saw this one doesn't because the numbers that start with a 1 oscillate in proportion between 1/9 and 5/9. This one doesn't, and to the alpha does not. So I want to say a few words now about some dynamical systems. Let's think of them as algorithms, iterated systems. You have an input, you start with an input, and you keep applying the same function, sometimes different. So let's think of the linearly dominated ones. This is joint work with Arnold Berger, who is now in the University of Alberta, and Leonid Bunamovich, who had Kolmogorov on his committee and was one of our great captures from the Moscow School of Probability at Georgia Tech. Now this is the complete theorem. There's nothing hidden here, but what I'd like to focus on is just these two examples. If you take any number and start multiplying by 2 repeatedly, it'll follow Benford's law. Any positive number. Stronger than that, take any number and that's not 0 and start iterating this function. So you just have a do loop. I start with x is equal to 1, and I calculate 2x plus this, and then I take that as input and keep calculating. This is much more complicated, but the leading term is the one which dominates here, and it says that even though this is as complicated as it looks, this sequence of numbers you get, this output, will follow Bemfer's law. It follows Bemfer's law base 10, but not base 2. If you multiply a number by 2, I should say now, also, George asked me before, do other bases work for Bemfer's law? Absolutely. Even base 2. Base 2 you have to think a little bit about. Every number which is not 0, the first digit is 1. So you're not saying anything. No, not about the first digit, but remember Bemfer's law is about the whole distribution. The second digit is not equally likely to be a 0 or a 1. Bemfer's law tells you the exact probability of those for all bases. So when you're multiplying by 2, a number, Bemfer's law doesn't apply. If you're looking at the mantissa, you start with a number like pi, multiply by 2. What's the new mantissa? Pi, base 2. Base 2 just shifts the decimal point from binary over 1. They'll stay exactly the same. Now here's the way the picture looks if you want to try to draw some pictures. I'm just graphing x over 2. Essentially, if a sequence of numbers follows Bemfer's law, then the reciprocal of it also follows Bemfer's law. So if xn follows Bemfer's law, 1 over xn follows Bemfer's law. Now I'm taking numbers which are going to 0. Think about it. These numbers are going to 0. I start with 1, these are all going to 0, monotonically. But the mantissas aren't going monotonically to 0. Suppose you start with 1, then you get 1/2, which is 0.5. Then you get 0.25, and then you get 0.6, something after that. So here you can see the pictures of these iterations. Here you start with a point here and just follow it around. Now notice that the key idea here is x over 2, if you're just looking at base 10, x over 2 is the same function as 5x. Because I'm just looking at the mantissas. I can multiply anything I want by 10, and it doesn't change anything I have to say about the mantissa. So if I multiply this by 10, I get 5x. So this is the picture you see. And on the log scale, you can start to see why it looks more uniform here. Now, nonlinearly dominated dynamics, now you're looking at functions which look like x squared or x squared plus 1. The situation here is a little bit different. Here, multiplying by 2, it is not going to be base 2. It's not going to be Bemford base 2. It's going to be Bemford base 10 and 7 and 5, but not 2. When you're squaring things, it's Bemford all bases. But there's exceptional points, unlike the linear case. By that I mean, when I said when you take any number starting and start multiplying by 2, I mean any positive number. Start with 1, start with the square root of pi, it doesn't matter. But if you're taking the square, it does matter. If you start with 1, you're not going to get Bemfer's law. If you start with a square root of 10, you're not going to get Bemfer's law. Because you square it once, you get 10, and then you're just looking at powers of 10, everything's 1 after that. So the conclusions here are, there are some exceptional points. There are a very small set of exceptional points. Measure theoretically, you'd say there are a set of measures 0. Probabilistically, that means if you're doing something randomly, the chance is 0 that that will happen. You start with a normal distribution, then square it. Start with a uniform distribution, then start squaring it. Anything like that, with certainty, with probability of 1, it'll follow Bemfer's law for all bases. Polynomials, square root of x does not follow Bemfer's law. That's clear because if I start with a number bigger than 1, we're taking square roots, it's going down to 1. Pretty soon everything's going to start with a 1 or 9 if I started with something smaller than 9. So I want to show you some functions which do and which don't. Now here you can see the same iterates I did before. We're looking at the function x squared, and I'm now restricting the mantissas between 1/10 and 1. So x squared is the function I'm looking at, but once I get out the, if I start with a smaller number right here, I'm below my mantis, I have to shift the decimal point over 1. In other words, I'm looking at 10x squared. So here you can see the exceptional point. If you start right here, it's going to stay there. If you start exactly right here, it's going to stay there. You won't have Pemberton's law. There's some points that doesn't work for it, starting points. But you can see that those starting points are very rare. In fact, there's only 2 of them in this picture. And here you can see how things are uniformly distributed on the log scale. And they're logarithmically distributed on the original mantissa scale. Now this goes back to the first question I asked. We answered the question about Ravi's game and how you can make money from friends using Pemberton's law. This goes back to the question I asked, what do you multiply by 2 or 3? You can do whichever you want, you can't destroy it. Pemberton's law is very robust. It's much more general than I'm stating here today, but here's an example. You can apply x squared, 3 to the x, or x to the x in any order you want. And it's going to follow Pemberton's law for almost all starting points. Now, I like this one because friends of mine tell me who do scientific calculations, tell me if you start with x is equal to 3, then no computer in the world can tell you the first digit of the 5th entry. So you can prove it mathematically here. So just think about it. If you start with 3, you got 3 to the 3, so you get 27, then 27 to the 27, and then taking that number, raising it to its power, you can't even say what the first digit is. But you can prove mathematically it follows Pemberton's law. Differential equations, for some of you who might be interested in that, here's a simple example. You have a very simple initial value problem. X dot is equal to minus f of x. X of 0 is x0. If f has a second continuous derivative, that's all that means. If the second derivative is continuous, if f prime of 0 is bigger than f of 0, which is equal to 0, so this is strictly positive, this is 0, then the solutions for this differential equation will follow Pemberton's law. So I wanted to say a few things about the continuous setting also. Stochastic sequences. Remember, another thing I wanted to answer for you is why does it appear in newspapers? They're not doing 2 to the n or iterating x squared plus e to the minus x. What's a good reason why Pemberton's law can be seen to appear in data like that that's seemingly random? And here's the best answer that I have so far. I'll define something called a p-random k-sample. It sounds complicated. I want to make you feel at ease with it. Here's what you do. You pick a probability measure at random in a natural way. Now that's a whole research topic that I'll talk about after the lecture if somebody wants to hear. How do you pick a probability measure at random in a natural way? You can pick one at random easily. I flip a coin. It comes up head, I use the uniform. It comes up tail, I use the normal distribution, the bell-shaped curve. That's not very natural. So there's natural ways to do it. So you pick one, you pick a probability measure at random, and I take a sample of size k. So the first 10 things, if k is 10, the first 10 things come from one distribution. And I pick a new probability measure, and I get another sequence of 10, let's say. And so on. Then the theorem is that if the way you're doing picking these probability measures is unbiased, it'll follow Pemberton's law with certainty. That's why I think that's the best explanation I have for the newspaper. When they wrote the USA Today articles today, they weren't looking at any numbers. Each article has some numbers in it. So the first article, one article here is on the crisis in Pakistan, one on the Chinese toy problem. So there's numbers in each one of these articles. So each article, within each article, it doesn't follow Pemberton's law. But the fact that I'm picking one story about this, another story about that, a third story about the third thing, putting these things together, you'll see it follows Pemberton's law. That's also very similar to his original data, Pemberton's data. Remember, he did square root tables. He did numbers from newspapers, physical constants, baseball statistics. Within the categories, they didn't fit very well. But you put all these together. You put baseball statistics together with square root tables and street addresses of famous people, another thing he had on the list. You put all these things together, it fits within 3 decimal points. For me, this is the theorem which explains it the best. You're mixing data from different sources. Now I want to spend a few minutes talking about applications in computer science. Hamming wrote that people used to think this was a gimmick, Bemford's law. He says, no, I'm going to give you applications in hardware, software, and so on. So he was talking about, for one thing, probabilistic analysis of round-off errors. So if you're implementing an algorithm, you're using Newton's method, for example. Newton's method follows Bemford's law. If you're using Newton's method to discover what a zero for a polynomial is, or a root of a polynomial is, solve a function, you have to give your algorithm some instruction on when to stop. So you can either say stop at time 1 billion, or stop once the errors are less than this. You have to have some reason for stopping. And when you stop, it's off a little bit. There's round-off errors. So in order to analyze the running time of algorithms, it helps to know what the statistical distribution is of the output. If it follows Bemford's law, that's a lot different than if it's uniform distribution. In fact, as Knuth wrote, if your assumption is that it was uniformly distributed, like you think, okay, I'm going to stop, I look at all these numbers, equally likely to be anywhere between 1/10 and 1, and you're calculating your estimated error based on that, you're underestimating. Because the real distribution follows Bemford's law, and that means there's a lot of numbers starting with 1, you're dividing by smaller numbers, and your average error is going to be 3 times as high, more than 3 times as high as you would have calculated otherwise. So this is, Hamming suggested it originally, Knuth wrote about it, also in his earlier, his 69 text also. Barlow and Barais in 1995, they designed a hypothetical computer. They said, look, if the numbers are really logarithmically distributed in almost all applications, you could design a logarithmic computer. So what does that mean? Informally, that means you don't need to allocate as much memory space to storing 9s as you do 1s. Now remember I said everything's true, so if you're using hexadecimal basis, Bemford's law applies for that. So I'm just using 1 base 10 for an illustration now. Feldstein, Goodman, and Turner were interested in predicting and analyzing overflow and underflow errors. That's, your computer is a finite state machine, so it only has the largest number that you can enter into it, an output, and the smallest one. If it goes over that, then you've lost control of your algorithm. You have no useful information from that. So they studied, they found inequalities, they found some nice sharp bounds, but they found that if it is logarithmically distributed, Bemford distributed, then the incidence of overflow and underflow is much more than you'd expect. So you have to be careful about that. Schotte, a German mathematician, studied Bemford's law in a round-off errors. He did the following calculation. He found that suppose your computer is restricted to use a basis which is the power of 2, so it can be binary, hexadecimal, whatever. He said, let's look at the following problem. So a colleague from another department brings in and says, I need to run this computer program. Please run it for me, which is what Knuth was doing. Please run it for me. You're going to need a certain amount of memory to run that program he had. The amount of memory is going to be dependent on his program. So the amount of memory you need is random, because you don't know who's walking in the door next. So suppose your objective is to design a computer so that the expected memory, on the average, the memory you need is as small as possible. He proved mathematically that the optimal one is use a base 8. Now this doesn't mean go start changing everything to base 8. This is just for the expected amount of storage you need. You might be interested in speed. You might be interested in accuracy. Abdallah, Howman, Julian, Perez, Gonzalez are looking at digital images to try to do fraud detection. Now there's a lot of interest, Homeland Security and everything now to know when photographs say are fake or altered, or other documents are fake or altered. They are trying to use Bemford's law. They found that the Bemford's law, the raw data does not fit it, but if they look at the gradients The gradients fits it, and one other property. So they found a particular kind of coding, so they want to test. Their objective there is both to know how you do efficient coding, and also how do you detect things that have been altered or not, have been changed. Arnold Berger and I just proved that Newton's method follows Bemford's law. This is surprising because Newton's method is 300 years old. Bemford's law is 125 years old. It's just surprising, main surprise is nobody put the two together before. And the conclusions for Newton's method are different, whether your root is a single root, a double root, or a root of multiplicity bigger than 2. So you get three different, slightly different conclusions. And of course, I have one here that I still haven't understood. I'm going to try to understand more this afternoon. Ravi has an application to context-free languages and several other applications in theoretical computer science. So now let me give you some general applications. This is one which is being used by meteorologists and zoologists. I've seen some applications from zoology. The idea is here. Is this. They have a lot of data, and they want to know, for example, does this come from one species or a number of subspecies? If you pick a probability measure at random, in fact, I didn't state, if you pick a single probability measure at random in an unbiased way, the chance is 0 that it'll follow Bemford's law. I mean, you had to pick Bemford's law. What are the chances of that? It's 0. So a single one won't follow it. So if they're testing things and they find it doesn't follow, if they find it does follow Bemford's law, my best guess to them, they ask, what does this mean? My best guess is they're mixing several different species or several different things. When you start mixing data is when you get it. A beautiful one, for testing mathematical models is this. Suppose you have a computer program that wants to predict what the populations of the counties in the United States will be 100 years from now. So you can have complicated Markov chain models, immigration factors, terms in it, use all kinds of Brownian motion methods, whatever you want. You have a very complicated math model, completely unrelated to Bemford's law. So here's a simple diagnostic test. You put in today's data, which happens to follow Bemford's law. We run it through your model, we see what comes to the prediction 100 years from now. If Bemford's law doesn't come out, then maybe you want to rethink the model or try to explain why suddenly Bemford's law won't be a reasonable distribution to model that with 100 years from now. And the beautiful one, of course, is this fraud detection marked in green. Let me give you actual data. You'll see how striking this was. This data didn't make up. This was published in the Wall Street Journal. I was very impressed that the district attorney of Brooklyn, New York, was reading scientific papers. He read this one marked in green and said, gee, maybe we can use that. And they caught and convicted 7 companies of fraud. They only looked at 103 of their checks. They said, let's see your checks. They looked at the checks. Now here's the Bemford's law. We've already seen that several times. Here's the true tax data. Very close, extremely close. These guys brought their checks in. Whoa. They had nothing starting with a 1. Nothing starting with a 3. So that doesn't prove anything. It just raises a red flag. That's why the IRS is using it. They'll look at your thing and say, sorry, you have too many 7s. Too many numbers start with a 7, come see us. They aren't looking for how your numbers start with a 7. Then they get into the more technical analysis of it. So it's a beautiful, very simple application. Random guess data is just an experiment I did at Georgia Tech. I asked 763 students, different classes, went around to all calculus students and gave them a slip of paper and said, write down a 10-digit, this 6-digit number, 8-digit number, I think, out of your head. They wrote it down, and I only looked at the first digits. Now, for a look at this 5 is very low. So it doesn't follow Bemford's law, but it's not uniform. 5 is very low. Why would that be? Well, these are all technocrats. Students in Georgia Tech are disgustingly technically advanced. They're way ahead of me. So they're thinking, well, 5, that's too much in the middle. You know, that's not an average number. Random number, I'll start with something else. So there's a whole set of research possibilities open there. Here's some of my favorite open problems. Nobody knows how fast things convert to Benford's law. Nobody knows it's a square number and add 1, and you start with 1 that follows Benford's law. That's a very simple one to state. Random maps and differential equations, general. And the last thing I want to do is just put up, should be called Newcomb's law, a lot of people think, so I want to give him his due. You know, we're making progress because we're standing on the shoulders of giants. And Newcomb was an incredible man. If you want to have an incredible read, just look at the website or something on him. He jumped ship, he ran away from home and jumped on a ship in Canada and came to the U.S. and started working his way up, became the fellow of all the Royal Societies of Europe and the U.S. And he won the Huygens Medal in Leiden, which is given not like a Fields Medal, not like the Nobel Prize. It's given once every 20 years, a gold medal. He won that for astronomy. He made major contributions to astronomy, including the speed of light. So I wanted to end with Simon Newcomb. So thank you very much for your attention. I understand there's a class in here, but I'll be glad to answer any I could now or afterwards. Bobby?
One quick question. The nonlinear dynamics case where there are an uncountably many exceptional starting points, do the ones that you, a couple of examples of those exceptional points you gave are the trivial ones in the sense that those are things that give you always one.
Right.
Are there any non-trivial
Yes,
starting
that's a good,
points
yeah.
that would be non-Benford?
And I was completely surprised by this one. I said if you square a number and add 1, square a number and add 1, square that and add 1. That's not easy to see that follows Benford's law. That's a hard proof. It only follows Benford's law almost always. I thought that there's no exceptional points to that originally. It just messes things up adding that 1 in there. That changes things eventually. But Arnold Berger found it, in fact, in our paper it's published, he found a concrete number, we wrote it out to maybe 25 digits. So when you square that and add 1, that number, every digit forever starts with a 9. And it's completely non-trivial. So yes, so you can find that in paper in the Transactions of the American Math Society. It's not trivial.